Hello everyone, welcome to my channel Physics Tricks. Let us study first law of motion in detail. So see here, what is first law of motion? I'll just give the rough idea about the first law of motion. If object at rest, it will remain at rest. If object in motion, it will remain in motion unless and until external unbalanced force acts on that body. So we'll study about each and every aspect of this law, right? So see here, Newton's first law of motion, and I took this from H.C. Verma and I'm reading it line by line. So see here, if the vector sum of all the forces acting on the particle is 0, so if you consider a particle and if vector sum of all the forces acting on the particle is 0, so if F1, F2, F3, F4, if you consider F1 plus F2 plus F3 and I'm adding it vectorially plus F4 must be equal to 0. So 0, then and only then particle remains unaccelerated, means what is the acceleration of the particle? It is 0 meter per second squared. Okay, now so and it is obvious, right? It is obvious that if net force is 0, acceleration must be equal to 0. Okay, if sum of all the forces on the given particle is F bar and its acceleration is A bar, the above statement may also be written as A bar is equal to 0 if and only if F bar is equal to 0, right? So A bar is equal to 0 if and only if F bar is equal to 0. Thus, if the sum of forces acting on a particle is known to be 0, net force is equal to 0, we can be sure that the particle is unaccelerated, that means acceleration is equal to 0, or if we know that a particle is unaccelerated, we can be sure that the sum of forces acting on the particle is 0. One under the same thing. If force is equal to 0, particle is unaccelerated, or else if we can say that if particle is unaccelerated, force on the particle is 0, right? So one under the same thing. However, the concept of rest, motion and acceleration is meaningful only when frame of reference is specified. Now, what is frame of reference? It is the location. It is the point from where we define all the motion parameters. What are the motion parameters? Velocity, speed, distance, displacement, time, right? All these are the motion parameters. So, frame of reference we have, right? Frame of reference we have is the point, location, right? From where we define all the motion parameters. Now there are two frame of reference are there, right? One is inertial frame of reference, other one is non-inertial frame of reference. So we'll study about that, right? That is when acceleration of the frame of reference is 0, that is inertial, and when an accelerating frame of reference is there, that is non-inertial. Okay. In general, different when measured from different frames. Okay, is it possible then that the first law is valid in all frame of reference? See, is the first law valid in all the frame of reference? For that, we'll consider an example. Let us consider the situation shown in figure 5.1. So over here, we have a figure, and that is 5.1. An elevator cabin falls down after the cable breaks. Okay, so this is the elevator cabin is there and which falls down after the cable breaks, supposed to be. The cabin and all the bodies fixed in the cabin are accelerated with respect to Earth, and acceleration is about 9.8 meter per second squared in the downward direction. Okay. So it is moving downward with an acceleration of 9.8 meter per second squared. Okay. Consider the lamp in the cabin. The forces acting on the lamp are, so if you consider this is the lamp, on this lamp forces acting are, one is the gravitational force, that is the weight of the lamp, and other one is electromagnetic force, that is the tension in the wire. Okay. Now the direction of W is downward and the T is upward. The sum W minus T is downward, right? Why? Because it is accelerating downward. Measure the acceleration of a lamp from the frame of reference of the cabin. But if you consider the frame of reference as cabin, it is the location, it is the point from where we measure all the motion parameters. So if you measure from the cabin frame of reference, it is W minus T is equal to 0. Right, W minus T is equal to 0 if we apply the first law. Okay, so the lamp is at rest with respect to cabin. the acceleration of lamp is 0, the person A who measures this acceleration is learned 1 and uses Newton's first law to conclude that the sum of forces on the particle is 0. Because with respect to this man, that is with respect to cabin, this man is seeing that this lamp is not moving at all. That means acceleration is 0. So W minus T must be equal to 0. Okay, that is W is equal to T. Instead, if you measure the acceleration from the ground, this lamp, now if you measure the acceleration from the ground, this lamp is moving downward with some acceleration, that is 9.8 meter per second squared. So this is W, this is T. That means this over here, W minus T is not equal to 0. Instead, if you measure the acceleration from the ground, the lamp has an acceleration 9.8 meter per second squared, thus is not equal to 0, and hence the person B who measured this acceleration concludes from Newton's first law that W minus T is not equal to 0. Right. If A measures acceleration and applies the first law, he gets W is equal to T. And if B measures the acceleration and applies the first law, he gets W is not equal to T. Both of them cannot be correct simultaneously. And this is obvious, right? Whether W must be equal to T or else W must not be equal to T. Now, who is correct? Who is correct over here? Person A or person B? At least one of the two frames is a bad frame, we can say. And one should not apply the first law in that frame. There are some frames of reference in which Newton's first law is valid, and this is very important statement. There are some frames of reference in which Newton's first law is valid. Measure acceleration from such a frame and you are allowed to say that A bar is 0 if and only if A bar is equal to 0. Understood? So there are some frames of reference in which Newton's first law is valid, and that frames are called as the inertial frame. So in the inertial frames only you are allowed to say A bar is equal to 0 if and only if A bar is equal to 0. But there are frames in which Newton's first law is not valid. There are frames in which Newton's first law are not valid. You may find that even if the sum of forces is not 0, the acceleration is still 0. You may find that sum of forces are not 0, then acceleration is still 0, or you may find that the sum of forces is 0, yet particle is accelerated in some of the frames, right? And just now we have seen sum of forces with respect to cabin is equal to 0, but still that lamp is accelerating, isn't it? Okay, yet the particle is accelerated. So the validity of Newton's first law depends on the frame of reference from which the observer measures the state of rest, motion and acceleration of a particle. A frame of reference in which Newton's first law is valid is the inertial frame, and the frame in which Newton's first law is not valid is the non-inertial frame. Okay, so Newton's first law thus reduces to definition of inertial frame. Why do we call it a law then? Suppose after going through this lesson, you keep the book on your table fixed rigidly with respect to earth. The book is at rest with respect to the earth. The acceleration of the book with respect to earth is 0. The forces on the book are gravitational force, one is the W, and the normal force, that is N we have. So can we write N is equal to W? Yes, you are allowed to write this. But yes, one thing that you need to keep in mind, and that is earth is also a non-inertial frame. Earth is also a non-inertial frame, right? The book is at rest with respect to earth. The acceleration of the book with respect to earth is 0. The forces on the book, as you can write over here, a very accurate measurement will give the answer no. But the earth is not strictly inertial. However, the sum is not too different from 0. Why? Because earth is also rotating about its axis. No. So if you place any object, there is a centrifugal force, or we can say non-inertial frame we have. But however, the sum is not too different from 0, and we can say that the earth is an inertial frame of reference for an approximation. Thus, for routine appears E bar is equal to 0 if and only if F bar is equal to 0 is true in the earth frame of reference. So this is the very important point. This is true only in earth frame of reference. This fact was identified and formulated by Newton and is known as Newton's first law. If we restrict that all the measurement will be made from the earth frame, indeed it becomes a law. If we try to universalize this to different frames, it becomes definition. So this is the difference between the definition and law. Right. For earth frame of reference, it becomes law. It is applicable everywhere. But if you universalize, means if you change the frame of reference, then it will become definition. That means it is valid till this only. Right. Definition means what? It is valid in a frame, right? In a certain things only. Right. We shall assume that unless stated otherwise, we are working from an inertial frame of reference. So this is all about the Newton's first law. We'll do one simple question based on the Newton's first law, and that is, a heavy particle of mass 0.5 kg is hanging from a string fixed with a roof. Find the force exerted by string on the particle. So force exerted by the string on the particle. So this is the tension we have. This is the mg we have. If you take the free body diagram of what is called as the particle of mass m, and as you can see, the forces acting on the particle is pull of earth, that is 4.9 Newton vertically downward, pull of the string T, which is vertically upward. The particle is at rest with respect to earth, which we assume to be inertial frame. Hence the sum of forces should be 0, that is T. If you consider vertically positive, then downward negative, 4.9 must be equal to 0. So T must be equal to 4.9 Newton. And this T must be acting in the upward direction. So this is the simple question which we have. So I hope this Newton's first law is clear to you all. Now if anyone has any doubt, they can always comment in the comment box. I'll try to reply to your comment as soon as possible. Thank you so much.